Hi viewers, in this video we'll solve problem 2.27 from the book Heat Transfer J.P.Holman 10th edition. Here is the statement of the problem. A house wall may be approximated as 1.2 centimeters layers of fiber insulating board, an 8 centimeter layer of loosely packed asbestos, and a 10 centimeter layer of common brick. Assuming convection heat transfer coefficients of 12 watt per meter square per centigrade on both sides of the wall, calculate the overall heat transfer coefficient for this arrangement. We have a composite wall that is made of fiber board, 8 centimeter of asbestos and 10 centimeters of common brick. Okay, so first of all, thickness of the fiber insulation is XF, so these are 2 in number, so its thickness will be 1.2 multiplied by 2, so the required thickness you will get, that is 2.4 centimeters. Convert that into meter, just divide it with 100, convert into meter, so it will be 0.024 meter. Okay, next is the thickness of the asbestos, that is XA, and its thickness is 8 centimeter and 0.08 meter. And then third insulations is the common break, that is 10 centimeter XP for common break, and that is in centimeter, so 10 divided by 100 to convert into meter, so it will be 0.1 meter. Okay, so thermal conductivity for fiberglass you can see from the table, but in exam it will be given in the statement or will be given at the end of the statement. So XF, that will be 0.038 watt per meter centigrade, and for asbestos thermal conductivity is 0.15 watt per meter centigrade, and for brick the thermal conductivity is 0.69, and at both sides of the wall, that is H1 and H2, the convection heat transfer coefficient is 12 watt per meter square. Okay, so let's say this is the wall whose first layer is made of, that is A to B, that is made of fiber insulating board. Then second layer B to C, that is of asbestos, that is XA. This is XF, that is its thickness, and then the third layer is of common break, that is XB, ABCD. So this C to D is XB thickness of common break, XA for asbestos, and XF for fiber insulating board. And this at this side, this is one side of the wall, this is the other side of the wall. The convection heat transfer takes place. So if I draw the resistance network diagram, here the temperatures will be given, and then resistance to the heat transfer is convection, then resistance by the fiber insulating board, then resistance by asbestos, and then resistance by common break, and then finally other side of the wall, and finally temperatures. The surrounding is T1, T2, but that is not given, so it is not our concern. We have to find the overall heat transfer coefficient for this problem. So here the resistance will be R1, here the resistance is RF, here the resistance is RA, this is RB common break, and this is R. Okay, so this R1 is and R2 is the same, because at both sides this is convection heat transfer coefficient of the wall, so its resistance must be the same because convection heat transfer coefficient is also the same, and it will equal to, remember in this formula we are using the resistance per area. So resistance per area means it is 1 divided by H1. We are taking the area common throughout. At the end it will be cancelled out. So don't get confused. When we reach to that point, we will clarify that. Don't worry. So it will equal to 1 over H1 or 1 over H2. Then RF is, okay, so this resistance R1, R2 is the same because at both sides it is convection heat transfer coefficient resistance. So that's why I can say that 1 divided by H1A. Now resistance of the fiber insulating board is equal to XF divided by KF. What is XF? That is 0.024 divided by KF, that is 0.038 divided by area. Area is the surface area. This is the surface that is unknown. Don't worry about it. Just write what things that is known. So after divisions you will get that is 0.6315 divided by area. Then RA, that will be equal to XA divided by KA and its area. So XA is 0.08 divided by KA, that is 0.154. Per divisions you will get its value, that is 0.52 divided by A. And next is RB, common break, that is XB divided by KB and area. So XB is 0.1, KB that is 0.69 A. So after divisions you will get its value, that is 0.154 divided by area. Okay, so now the overall heat transfer coefficients and area product is equal to 1 divided by total resistance that is offered to the heat transfer, that is R1 plus this R2, then plus this RF, RA, RB, RF, RA plus RB. Okay, so overall heat transfer coefficient area is equal to 1 divided by, what is R1, that is equal to 1 divided by 12A. So 1 divided by 12A plus 1 divided by, so it's R1, R2 are equal, 12A plus RF 0.617 6315 divided by A plus 0.52 divided by A plus 0.1545 divided by A. Now take a common and divide with A. So this A will be cancelled out with this whole each terms of A. So you will get overall heat transfer coefficients, that is 1 divided by 1 by 12 plus 1 by 12, it become 2 by 12 plus 0.6315 plus 0.52 plus 0.154. So after doing simplification, you will get the overall heat transfer coefficient U, that is 1 divided by 1.4635. After simplifications, you will finally get its value, that is 0.684 watt per meter square centigrade, and that is our final answers. This is the overall heat transfer coefficients that is occur across this composite valve. I hope you understand. If you still have any confusion, you can ask in the comment section.